Valence shell electron pair repulsion, more simply known as VSEPR, is a relatively simple way of talking about and predicting the shapes of molecules. The basic idea is that electrons want to get as far away from each other as possible because they repel each other. How far apart they can get depends on how many of them there are. We call each region where there are electrons an electron domain. Any unshared pair of electrons is a domain, and any bond, single, double, or triple, is also one, but only one, domain. There are 5 different electron domain geometries, formed from 2, 3, 4, 5, and 6 electron domains. You need to memorize the number of domains in each shape, the names of the shapes, and the angles between the domains. 2 electron domains result in a linear geometry, as the domains separate by 180 degrees. 3 domains result in a trigonal or triangular planar geometry, with the domains separated by 120 degrees. With 4 domains, the domains take on a tetrahedral geometry, which has angles of 109.5 degrees. This 3-dimensional arrangement has the domains separated by greater angles than if 4 domains were in the same plane, where there would be 90-degree separation. 5 domains produce a trigonal bipyramid geometry. This has 3 domains in a plane and 2 perpendicular to the plane with 2 distinct angles. The 3 domains in the plane are separated by 120-degree angles, and the 2 perpendicular domains have 90-degree angles with the ones in the plane. With 6 domains, the domains have an octahedral geometry, with domains pointed in opposite directions on the x, y, and z axes, and all angles 90 degrees. In order to determine the electron domain geometry, simply count the number of domains, bonds and unshared pairs. The domain geometry is the geometry for that number of domains. Molecular geometry is a bit more complicated than just finding the electron domain geometry, however, because the shape of the molecule is determined by the positions of the atoms only, and the unshared or non-bonding pairs of electrons are ignored. This means that there may be several molecular geometries possible for each electron domain geometry. The example given shows the 3 molecular geometries that have a tetrahedral domain geometry. We will return to this later. In addition, while the basic bond angles are determined by the electron domain geometry, non-bonding pairs and bonding pairs do not have the same effect on the positions of the atoms. Bonding pairs are bound at both ends of the bond, where non-bonding pairs are bound only on one end, near the nucleus of the central atom. Therefore, the non-bonding pairs take up more space and exert more repulsion, so the presence of non-bonding pairs will squeeze the bonding pairs closer together, decreasing the angles between them. We see this for the series CH4, which has only bonding pairs, NH3, which has 1 non-bonding pair, and H2O, which has 2 non-bonding pairs. The bond angle decreases from 109.5 to 107 to 104.5. These are all close to the basic bond angle for a tetrahedral domain geometry. In addition, the presence of a double bond with its additional electron density will squeeze the single bond domains closer together. Both of these factors will cause the bond angles in the actual molecules to deviate from the angles in the electron domain geometry. Now we will walk our way through the 5 domain geometries to see what the possible molecular geometries are. To distinguish them, we will look at the number of domains and divide them into bonding domains and non-bonding domains. We will give a name to that molecular geometry and an example of the molecule that has that geometry. We begin with the linear domain geometry with 2 domains. The linear electron domain geometry has only one possible molecular geometry, linear. Any molecule with only 2 atoms must be linear, regardless of which electron domain geometry is present, since 2 points determine a line and you only have 2 points. The trigonal planar domain geometry has 2 possible geometries. Trigonal planar if all the domains are bonding domains, and bent with an angle near 120 degrees if one domain is a non-bonding domain. The tetrahedral domain geometry has 3 possible molecular geometries. If all 4 domains are bonding domains, the molecular geometry is tetrahedral. With 3 bonding domains and 1 non-bonding domain, the molecular geometry is trigonal pyramidal, sometimes called a flattened pyramid. With 2 bonding domains and 2 non-bonding domains, the molecular geometry is bent with angles close to 109.5 degrees. For the trigonal bipyramid domain geometry, things are more complicated. There are 2 distinct positions in the geometry. The 3 domains in the same plane are called equatorial, and the 2 domains perpendicular to the plane are called axial. It turns out that there is less repulsion if the non-bonding pairs are placed in the equatorial positions than if they are placed in the axial positions. Specifically, a single non-bonding pair in an equatorial position has 90-degree repulsions with only 2 bonding pairs and 120-degree repulsions with 2 pairs. If placed in the axial position, it has 90-degree repulsions with 3 bonding pairs. The situation is even more pronounced when there are 2 or 3 non-bonding pairs. So the general principle is that the non-bonding pairs go in the equatorial positions. This gives rise to 4 molecular geometries. No non-bonding pairs, trigonal bipyramidal geometry. 1 non-bonding pair, seesaw geometry. 2 at close to 120 degree angles and 90 degrees from the other 2. 2 non-bonding pairs, T-shaped geometry. 2 close to 180 degrees apart and the other at 90 degrees from both. 3 non-bonding pairs, linear geometry. For the octahedral domain geometry, there are 3 molecular geometries. It might seem at first that there would be more, but any structure with more than 2 non-bonding pairs would have to have started with more than 8 electrons in its valence shell, which does not happen. The 3 molecular geometries are no non-bonding pairs, octahedral geometry. 1 non-bonding pair, square pyramidal geometry, with angles slightly less than 90 degrees. 2 non-bonding pairs, square planar geometry, with 90-degree angles.